All right, we're going to finish off section 2.3 with an important limit. So this is a very specific limit that is going to become important to us later in chapter 3. And it's not an obvious one. The limit is the limit of as x approaches 0 of sine of x over x. So sine of 0 is 0, as you may recall. And so we'd have 0 over 0 there, another indeterminate form. But unlike some of the examples we did earlier in this section, there's no algebraic simplification that can be performed to cancel out the x factor. Right? This is the sort of limit that is really tricky and that we need to get sort of creative to figure out. Turns out this is equal to 1. All right? So we're going to prove this fact, that this limit is 1. Okay, it can be verified graphically or numerically, right? If you just pull up Desmos, you can look at this graph and say, yes, that does appear to be approaching 1. But a true proof of this fact is going to get a little more in depth. Now, this proof is in the textbook, and you can read through it there. I'm going to go over it in sort of my own way with color-coded pictures and that kind of thing. I just really like walking a class through this proof because it serves to really like explain some. Well, it serves to give us an opportunity to like dig into geometry and trigonometry and just really see the like workings of all the math kind of fitting together perfectly, just to give us something that we need. And it's a really neat application of the squeeze theorem. All right. You're not you're not going to be doing something quite like this on any of your assignments. So you're not going to need to be able to reproduce a proof like this one. So don't worry about that. Just focus on learning about the concepts and how they're applied, and sort of getting a little bit of a maybe geometry refresher out of this. Okay. So first I want to pull in, we're going to do the proof in a moment, but first I want to pull in these two geometric formulas that we're going to need for this. So one is the area of a triangle, 1/2 base times height. That's pretty familiar. I imagine most people probably remember that one, but the area of a sector is another formula you learned in when you took trigonometry. Probably right near the beginning of your trig unit, you learned about area of a sector is 1/2 times the radius squared times theta, where theta in particular is in radians. I don't think I've said it yet, but in this class, angles will always be in radians. If they're not, if you encounter like a homework problem where the angle's not in radians, I recommend converting it to radians immediately, because when you're doing calculus with like sine and cosine and other trig functions, you really need your input variable to be in radians in order for things to work out nicely. If you don't, you kind of have to always be keeping this conversion factor around, which is kind of annoying. So we're going to stick to radians as much as possible in this class. All right, so I'm going to set those two formulas aside. Let's dive into the proof. First, it is equivalent to say that we're talking about the limit as theta approaches 0 of sine of theta over theta, and that equals 1. Okay? But hang on, x and theta aren't the same thing, right? X is the x-axis and theta is an angle. Well, no. It doesn't matter. They're both real numbers, right? Like along the x-axis, you're measuring out real numbers, and when you measure an angle, that's a real number as well, right? So it doesn't matter what you call that input variable. It's the same limit no matter what. So I'm just rephrasing it in terms of theta, because I would like to, for the purpose of this proof, think of that number as an angle, and that will be useful. So next, we're going to suppose that theta is a positive angle in radians. In particular, we're going to go with a small positive angle in radians. all we really care about is approaching 0, right? So we can assume that the angle is small, because if it's big, it's far enough away from 0 that we don't really care. Like the limit only is going to be determined by what's going on as we get closer to 0. So we might as well assume it's small. And that'll make our pictures easier. We're going to have that angle be in the first quadrant, okay, between 0 and pi over 2. Now, I did say positive, and in order to figure out this limit properly, we should approach 0 from both the right and the left. We're only going to do half the proof where we're approaching from the right, but if you just drew some similar pictures with a small negative angle, you would get the same result. So it's like the two halves of the proof are almost identical. We're going to do one of them, and you can try the other one on your own if you'd like. So let's draw a picture. We now have a angle which is some smallish positive angle. Let's say it's like that. Okay, so there's our theta right in there. Now, let's make this a unit circle right here. So this distance right here, from the origin to the edge of the circle there, that's a radius, so that's going to be 1 unit long, right? This point on the circle, where this ray at angle theta intersects the unit circle, remember from trigonometry that the coordinates of that point are given by the cosine of theta and the sine of theta. So in particular, the y-coordinate, or the height of that point right there, is given by sine of theta. So I'm going to label that distance sine of theta. Okay, I hope it's not too small. So that distance is sine of theta, and that's at a right angle to the this x-axis. The other fact I'm going to put in here that is a little more obscure, you might not remember this one. If I drop a vertical line down at a right angle again to the x-axis, so that it meets this point on the circle, tangent to, like, just it's tangent to the circle right there. If I drop that line down from this ray, then that distance is actually given by the tangent of theta. So if you didn't remember that, that's okay. It's one that I often forget as well, but we're going to use that fact this time. So there's like 3 different shapes going on inside here. What we are going to look at is the relative areas of those 3 shapes. So one of the shapes we're going to look at is I'm going to draw 3 more circles here. I got to get my unit circle 3 times. Okay, so one of the shapes we're going to look at is the big triangle that includes this edge here of length tangent theta. So that big triangle right there, it's a right triangle. That's one shape we're going to look at. That's the biggest of the 3 shapes. The middling of the 3 shapes is going to be the sector. The sector of the circle right here, that like pizza slice. That is the middle of the 3 shapes. Its area is in the middle. And then the smallest of the 3 shapes is given by it's like we're going to build the sector, except instead of having that arc as the edge of our shape, we're going to draw a straight line and cut off that arc like that. Pow. Cut that off. And make a little triangle. So we can tell that this is the biggest one and the green one over here is the smallest one, because these shapes are like contained within each other. So that purple triangle entirely contains the red sector, and the red sector entirely contains the green triangle, right? So these areas are going to be related to each other by these inequalities, like this, with the biggest one on the left here. I've put it in this order so that it's going greater than or equal to, and this, from bigger to smaller, on purpose. We're going to end up reversing that order kind of at the end, but wait for it. All right, so now let's use our formulas. All right, I'm going to smooth this up a bit. So for this area of a triangle, we're just going to use 1/2 base times height. The base of this triangle here is of length 1, and the height is tangent theta. So 1/2, 1 times tangent theta is going to give us tangent of theta divided by 2. So that's from the area of a triangle. Next, the sector, 1/2 times the radius squared times theta. Well, the radius is 1, and this is theta in here, so that's going to be 1/2 times 1 squared times theta, or just 1/2 theta. Let's just write that actually as theta over 2. So that's from the 1/2 r squared theta calculation, giving us the area of that red sector. And then finally, for the area of this small triangle, again, we'll do base times height. The base is of length 1, and the height right here, that's the sine theta, right? The height of that point right there on the unit circle. So this is going to be 1/2 times 1 times sine theta. Or in other words, let's just write that as sine of theta over 2. All right, so now we have our inequality. Now, the first thing we can do is multiply everything by 2 and cancel out all the 2's, right? So we'll do that. That'll cancel all our 2's. Pow, 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 pow. Whoopsie daisy, there's the 2. Almost crossed the sign out. So now we have tangent of theta is greater than or equal to theta, which in turn is greater than or equal to sine of theta. And the next thing we want to do kind of comes out of nowhere, but what we want is to divide everything by sine of theta. For small positive angles, this is okay to do because sine of theta will be a positive number. And so that's not going to mess up our inequalities at all, okay? Remember, we're in quadrant 1. So sine and theta are both, sine and cosine are both positive. All right, so a little bit of trig review. We may remember that tangent is sine divided by cosine. So if we divide by a sine, we're going to be canceling out a sine, and we'll get 1 over cosine of theta. In the middle, we have theta over sine of theta. And then on the right here, sine of theta divided by itself is going to be 1. So let's start from there. I'm just going to move on here. I'm going to rewrite what we have. So far, we've got 1 over cosine of theta is greater than or equal to theta over sine of theta is greater than or equal to 1. So that's where we have gotten to. Now the next step is a bit of a weird one, a bit of an obscure fact, but if you have this inequality involving fractions, if you reciprocate all those fractions, then it flips the inequality around. Like 2 is less than 5, but 1/2 is greater than 1/5. If you flip them both upside down, I'm gesticulating in the air here, sorry, that's probably not helpful. If we reciprocate all of these fractions, then the inequalities are going to just turn around. So I'm going to write this as cosine of theta is less than or equal to sine of theta over theta, which in turn is less than or equal to 1. And now I think you can see we're getting close to what we want. Because remember, we want to know the limit of sine of x over x, right? And now that we've flipped this upside down, we have basically sine of x over x. So let's examine the limit as x approaches 0 of the functions on the left and the right. We'll switch back to x now instead of theta. So the limit as x approaches 0 of cosine of x, this is nice and easy. Remember, cosine at 0 is meeting at a peak, one of its peaks, and that is up there at height 1, so that limit is 1. And so that's the limit of the function on the left, which is the smaller one. The limit as x approaches 0 of 1, well, that's a constant function, so that's going to equal 1 as well. Aha, these are the same. So our function that we're interested in, sine of x over x, which is bounded, it's always greater than or equal to cosine of theta, but less than or equal to 1. And those two functions are coming together. They have the same limit as x approaches 0. That means this sine of theta over theta is getting squeezed in between them. So we can finish by saying, by the squeeze theorem, we know that the limit as x approaches 0 of sine of x over x also equals 1. And we did it. Yay! Wow. So that proof, that whole proof is very different from the algebraic manipulation type problems that you're going to be doing in the homework. It's applying the squeeze theorem, but in order to get to the squeeze theorem, in order to get to that inequality to which we used for the squeeze theorem, we had to do all this geometric reasoning, right, about areas with the relative size of areas, and then calculating what those are using trigonometry. So I just love how all these pieces come together. This is a beautiful proof. I hope you enjoyed it. We're going to take this limit and use this later to prove some pretty neat stuff about the sine function. So hold that thought, and we'll pull this back out when we need it.